We found you, Ryuga!
We would like you to come with us quietly, please. But we'll take you with us by force if we have to.
Infants!
What? He used his hand!
Huh? He's making fun of us! Ah! What is going on?
His base spin is somehow increasing!
When I was a kid and saw this scene from Beyblade for the first time, I thought it had to have been some fantasy magic at play. In case you didn't notice, this person span his Beyblade counterclockwise. At the time, every single other Beyblade in the show span clockwise. Just because you span left should not let you steal the spin from the collision of others. Trying this in real life, we're going to spin this Beyblade clockwise, and then we're going to hand spin this blue one counterclockwise. And let's see if it can spin steel. So this one is clockwise. And this one will be counterclockwise. Well, it still lost terribly. So even if it did spin steel, it was not as much as the anime version. However, in a later episode, there was an actual physics-ish explanation of how it was spin stealing.
El Drago absorbs power from its opponent's attacks!
It's the power of the rubber-coated energy ring! The rubber on El Drago's energy ring acts as a cushion, and it absorbs the opponent's power! So no matter how many attacks it takes, none of them will be able to stop it from spinning!
And then El Drago changes the stolen power into power for itself! It's hard to beat for sure!
So they're saying rubber is the difference maker here. Unfortunately, I don't own that Beyblade with a rubber ring, and my Beyblade, as you can see, is all metal around. But what I can do is take a rubber band and wrap it around the metal frame. Just like that, the rubber band is now wrapped all around the metal ring. And now, let's put it to the test. Just like earlier, we're going to release this one clockwise and the newly wrapped Beyblade counterclockwise. And spinning this counterclockwise. Turns out it wasn't magic after all. So how did the rubber band become the difference maker? To do that, we have to talk about momentum. In high school, you have probably dealt with linear momentum, which is the product of an object's mass and velocity. However, since we are talking about spinning objects, we have to switch over to rotational or angular momentum. It is defined as the product of an object's moment of inertia and its angular velocity. You can think of the moment of inertia as how hard it is to spin up a rotating object. It does the same thing as mass for linear momentum, both representing the resistance to change. Hence, the moment of inertia contains mass as a variable, where for a spinning disk it is equal to 1 over 2 mr squared. On the other hand, angular velocity is simply how fast it is spinning. Because they are both conserved, we can solve for final angular velocity in a very similar way to final velocity for linear momentum. This makes the proper term not actually spin steal, but spin equalization, as the stealer won't actually get faster than the opponent. Shouldn't two opposite forces stop each other? Well, if you focus on the point of contact in the middle, the forces are actually in the same direction. So let's say this one is spinning its counterclockwise, and this one's spinning its clockwise. See how they're actually both spinning upwards from the middle and pointed up. Whereas if it were the same direction, in the middle, at that point of contact, they're actually opposite. This one's going downwards and this one's going upwards. The only problem is that we also need to take account the time of the collision, impulse, as the Beyblades do not become equal in speed after a 5 millisecond collision. As we saw, it took several collisions before they reached the same speed. Impulse is defined as the change in momentum. For linear, you multiply the force by the time, whereas for rotational, you multiply the time by the torque. This is where the rubber band finally comes into play. By having a higher friction than metal, it generates a larger torque, allowing for that spin steal. One thing to note though is that this friction force is also dependent on the difference in speed. The bigger the difference between the opponent and the stealer, the greater the sliding speed and the larger the friction force. That is why, if you were to go for a spin stealing strategy, you may want to launch your Beyblade with a lower initial velocity on purpose, or even hand spin it. To showcase this time we're going to time how long this can spin by itself, and we're going to time again how long it spins with the other Beyblade in the stadium. But that Beyblade will be hand spun. This will keep being launched at full power. That's actually kind of weird that it stayed standing well after stopping. Around a minute and 50 seconds. Now let's try that again with another Beyblade in the stage to help it spin steel, despite this one spinning much faster than the other one. As you can see, it actually lasted shorter than it did without a Beyblade to spin steal from, which means it was actually getting spin stealed from because it was the faster Beyblade.